Hello dear students, welcome you all. In this lecture I am going to discuss about the pulse code modulation, right? Pulse code modulation is basically a digital modulation technique, right? In which we are, finally representing the information in the form of digital signal, right? In that we have, you can see here the signal in PCM are binary. They are represented by binary numbers, bits, either with 1 or 0, right? We have already studied the different pulse modulation techniques earlier. They were analog in nature, right? You can have studied pulse amplitude modulation, pulse width modulation, pulse position modulation, but all of them were analog modulation techniques, and these were actually very prone to the noise. So that's why we are preferring this digital modulation technique, that is called pulse code modulation, right? And in this we have advantage of very less noise as compared to the analog modulation techniques, and it is easy to process the digital signals as compared to the analog signals, right? So in this lecture we are going to cover this particular topic, pulse code modulation. Pulse stands for the pulse that is going to take the sample of the information. You can see here that in digital electronics, pulse is represented in this way, right? So pulse means we are taking this pulse, let this is the information signal. You can see this is the information signal f of t, and this is the high frequency carrier pulse train, right? This carrier pulse train is going to take the sample of this information, and that process is called sampling. We have already learned about the sampling. We have learned about the sampling theorem, right? Nyquist rate, all these things. So we will take the sample of this information, then these samples will be quantized, and finally they will be encoded in the form of numbers, binary numbers, and that will be the representation of the information in the format of digital, right? Or we can say that will be a digital signal, and then that signal will be sent through the transmission line, and it will be received at the receiver end, and again that signal will be decoded and the original information will be recovered. So this is the entire scenario of pulse code modulation. Pulse stands for this pulse, code means encoding, modulation means this information is modulated with this pulse train, right? So I'm going to the next slide. You can see this is these are the different steps that that are included in the PCM, right? So you can see here the PCM signal consists of three main steps, right? It starts with the sampling. As I told you that the first step in the PCM generation, pulse code modulated signal generation, is a sampling. Then we have a quantization, and then have a encoding. I told you earlier that this is the process. It is a three-step process: sampling, quantization, and binary encoding, and then that will give me the digital signal. You can see here a PCM generation. So you can see here, this is the original information, analog signal. You can see here that analog signal is sampled first by the sampler, right? Then it is quantized, and then after it is encoded, and when I encoded this signal, this is the resulting output. This is now digital signal that is ready for the transmission, right? So you can see here the different steps, right? This is a pulse amplitude modulated signal, right? That we got after sampling. We have already learned about the pulse amplitude modulation. Pulse amplitude modulation means the I am explaining you here once again. Let this is the information signal and this is the periodic pulse train. So when we are doing the pulse amplitude modulation, we are actually what we are doing? We are changing the amplitude of these pulses in accordance with the message signal, right? So you can see here in this diagram, pulse amplitude modulated signal, right? You can see that the amplitude of the different pulses is different. So this is what done by the sampler, right? Sampler took the sample of information signal, and this signal, resultant signal, is a pulse amplitude modulated signal. Then after it is sent to the quantizer, right? We will learn what is the role of quantizer, and then finally it is sent to the encoder for encoding, right? So let's go to the next slide. So you can see the different steps that I explain you here. Right. So before we sample, we have to filter the signal to limit the maximum frequency of the signal as it affects the sampling rate. This is the first process. First of all, the information signal will be passed through a low pass filter, right? We know what is the role of low pass filter. It will allow the passage of a particular range of frequencies, and all the frequencies that are above that range, they will be eliminated. So then after filtering, the signal will be sampled. You can see here, filtering should ensure that we do not distort the signal. We only remove the high frequency component that may not affect the signal shape, right? What I said, that we are only removing the high frequency component in the information signal, right? Then after that, signal is sampled. The process of generation of pulses of finite width, you can see, and varying amplitude equal to the instantaneous amplitude of the analog signal. I told you this, right, that the amplitude of the pulses will change in accordance with the analog signal, or we can say message signal. This is called sampling. The number of pulses per second is called sampling rate. So we know, we have learned that according to Nyquist criteria or sampling theorem, Fs, sampling frequency, should be greater than 2 times the maximum frequency component present in the information signal. We have learned about it, right? So this condition is satisfied during the sampling, right? So this is sampling. Going to the next slide, you can see here. Right. So next step, when we took the sample, then the next step is quantization. You can see here, quantization. Now you look at this, sampled PAM signal. I will call it as a PAM, pulse amplitude modulated signal. So you can see this signal. Now the amplitude of the these are the amplitudes. The different pulses is not quantized. It can have any value. And what is the value? Value of the either voltage or you can say current. So when we are representing the amplitude in terms of voltage, you can see the voltage level of the sampled signal can have any value, right? So we are going to do the quantization. I mean, if suppose this value of amplitude is 1.3 volt, or we can say 2.2 volt or 3.7 volt at any particular instant, it is 5.6 volt, like that. So what we will do in the quantization? During the quantization, we will convert the amplitude of the signal to the nearest predetermined level, right? So for 1.3 I will call 1 volt, for this 2 volt, this 4 volt, this 6 volt, right? In this way. Now this choice of the conversion, this is very important here. The choice of the conversion or rounding off of the this voltage level depend upon the number of bits that we are going to use in the encoder, right? Suppose I'm going to use 3 bits, right? 3 bits, 0 0 0 0 0 1, right? 0 1 0 0 1 1. This is for 0 volt, this is for 1 volt, this is for 2 volt, this is for a 3 volt, like that, right? So if I am using I'm going to use the 3 bits for the representation or encoding of the information. In that case, the voltage level during the quantization will be from 0 to 7 volt, right? Because we can use the 3 bits only up to 0 to 7. When we go to the 8, we require 4 bits for the representation. We know that 4 is 8 is represented on the binary scale as 1 0 0 0, right? So it means we have to have 4 bits for the representation. So it is totally the choice how many number of bits we are going to use during the encoding. If we are using 3 bits, then obviously we are fixing the voltage level from 0 to 7 volt. If we are using 4 bits, then 0 to 15, because we know very well that from 0 to 15 or I can say 7 to 8 to 15, I require 4 bits, right? Then after, the number of bits again increase. So this is the way. So this is quantization. Clear? We will round off the amplitude to the nearest predetermined level of the voltage, right? So this is quantization. Now this is next step is encoding, right? So you can see here encoding. So encoding means now as I told you, suppose I have converted the voltage levels of the PAM signal as a 1 volt, 2 volt, right? 0 volt, 7 volt. So what I will do during the encoding? During the encoding, I will convert these predetermined voltage levels into the corresponding bit stream. If I am using 3 bits, then 0 0 1, 0 1 0, 0 0 0. Similarly for 7, right? 1 1 1. This is the way. You can see here quantization intervals are coded in binary form, and so the quantization interval will be the power of that I told you, that how many number of bits we are using. These numbers can be represented by 3 4 5 6, so number of bits respectively. The output of the Pulse code modulator is thus a series of binary number, it represented by some power of bits, right? Now the next is bit rate and bandwidth requirement. Now the bit rate of a pulse code modulated signal can be calculated from the number of bits per sample multiplied with the sampling rate, right? So bit rate is equal to number of bits per sample. So if here we are using 3 bits per sample, right, in this particular case, so it will be 3 bit multiplied by the sampling rate, fs. So it will give me the total bit rate, right? I can calculate the bandwidth required to transmit the signal depend upon the type of line encoding used, right? So here we can see that in pulse code modulation we are using either 3 4 or 8 number of bits for the representation of information. So obviously the bit rate required is high, and somehow the bit rate is linked with the bandwidth required for the transmission of a signal. So if I am using large number of bits, then obviously the bandwidth required will increase. So I have to pay the price for that, right? Otherwise, we have seen that a digital signal always need more bandwidth than the corresponding analog signals. But we know very well that the digital signals has lot of advantages, other advantages, particularly in the form in the case of immunity to the noise, right? So we have to pay the price for it. But this is a drawback for pulse code modulation, that it require a very high bandwidth, right? And when bandwidth is high, we have to pay the price for it, right? Now, next step is PCM decoding, right? As I told you, that when the signal is recovered at the other end, then it is again decoded, and it is then the original information is then recovered. So, for the PCM decoding, pulse code modulated signal decoding, the circuit that is commonly used is a sample and hold circuits, right? Sample and hold circuits, you can see here, right? We use a hold circuit that hold the amplitude value of the pulse till the next pulse arrive. We pass this signal through a low pass filter with the cutoff frequency that is equal to the highest frequency in the pre-sampled signal. The higher the value of quantization level, right, less distortion signal is recovered. So what they are saying, that the first of all, the signal is passed through a low pass filter, right, to remove all the wanted or undesirable frequencies from the signal, and then after these signals will be passed through a low pass sample and hold circuit, right? So then after this sample and hold circuit is nothing but I can say here that in simple forms it is a combination of PN junction diode, right, and a resistor, right, and a capacitor. This is the simplest example of a sample and hold circuit, right? Otherwise, in reality, this entire circuit contains lot of other elements also, but this is the working or functional unit of a sample and hold circuit. What it will do when the PEM signal will pass through here during the rising part of the PEM signal. This PN junction diode will become forward wise, and it will charge the capacitor, right? But when there is no input at this junction diode, then it will behave like a open switch, and during this time this capacitor will hold the charge on it and will produce corresponding output. So in this way we can estimate that the output will follow the voltage across these two terminals, will follow the envelope of the message signal, right? If this was the message signal PCM signal that has arrived at the decoder, then we can say that this envelope is following the, right, this envelope is the information. So when this is passed through here, as I told you, during the rising part, or we can say positive, when this is positive and this is negative, this will become forward wise, but when it is negative and this is forward, it will become reverse wise, behave like a open switch. So in this way the voltage across this these terminals, it will follow the envelope of this sample this PCM signal, but in reality it contains a lot of distortions that are removed after many steps, and finally we are able to recover the information, right? You can see here it was a digital information input signal, that is this, then it is a PCM decoder, it is passed a low pass filter, then it is passed to the further this sample and hold circuit, and then after we are getting the you can see here we are getting finally the message signal, right? You can see here this is the final message signal that is recovered, right? Now here I have taken a question, right? The bandwidth of a TV signal is 4.5 megahertz. If the signal is converted to PCM bit stream with 1024 quantization level determine the number of bit per second generated by the PCM signal. So here FM is 4.5 megahertz, right? Fs is equal to 2 FM, the sampling rate, right? So 2 into this samples per second, right? And then after calculation, we got 9 into 10 raised to power 6 samples per second, right? So this is the solution, right? You have given a TV signal whose bandwidth is 4.5 megahertz, right? So if I want to sample this signal, then according to sampling theorem, sampling rate should be greater than 2 times the bandwidth, right? So 2 times this, then sampling rate is equal to this, right? Now you can see here that they have also given that the quantization level is 1024, right? So you can see now here quantization level is 1024. So number of bit required to encode a sample can be calculated 10, right? Quantization level 1024 means the number of bits required, we can calculate the number of bit required for this as this. Right? So here now you can see quantization level is given as a 1024. So number of bits required to encode the sample can be calculated as a this is the formula. So number of bits required is a 10, because 2 raised to power 10 that will give you 1024, right? Quantization levels. Quantization levels means they are labeled in the signal is labeled in 1024 base. This is the meaning of it, because I have told you that if I am encoding the signal from 0 to 7, then the quantization level will be 8, right? Means I am encoding the signal in a 0, 1, 2, 3, 4, 5, 6, 8 ways. If I am taking it as 0 to 15, then it means the quantization level is 16. The number of bit required is equal to 3, number of bit required is equal to 4. So this is the way. So here you can calculate the number of bits required, they are 10, right? So number of bits generated per second by the PCM encoder can be given as bit rate is equal to n into sampling rate. So this is the answer, right? 90 megabytes per seconds, right? So this is the solution to this question that was asked, that the bandwidth of the signal is this if the signal is converted into bit stream with 1024 quantization level, determine the number of bit per second generated by the PCM system, right? So first of all, we calculated the sampling rate, then after we calculated the bit rate. Bit rate is number of bits multiplied by the sampling rate, right? Advantages of PCM, pulse code modulation. It is robustness to the noise and interference, compatibility of different classes of tariff in the network, effective regeneration, secure. So all these are advantages of PCM, right? Now I am going to the disadvantages. You can see here disadvantages also. So disadvantages includes, in linear quantization, the distortion is more, and to decrease the distortion, the number of levels in the has to be increased. But this is a drawback. If increase the number of levels, the bandwidth requirement will also increase, right? So this is the main problem that I discussed in the beginning, right? If I want to reduce the distortion and noise, I have to increase the levels of the representation of the information, but that again create another problem, the bandwidth requirement, right? So this is the drawback. And application, as far as applications of PCM are concerned, it is compact disc, digital telephony, we can use it, digital audio applications I can use it, but actually in reality it is rarely used because of these drawbacks. I am showing you one more drawback of the pulse code modulation. I was talking about the another drawback of PCM signal. You can see here it is a pulse code modulated signal, right? So you can see here this sample is encoded as 010, this is encoded as 100, this is encoded as 101, right? The entire process you can see here. These are the predetermined voltage level. Here we are using 3 bits from 0 to 7 that I talk about in this lecture, right? But you look at this and the sampled or the final digital output of the PCM. Now you go through this one, and this one, same, right? Same 110, 110, 110. Now this is creating a problem. How it is creating a problem? Because these 3 samples are same, and they are increasing the number of bits required for the transmission. They are increasing the bit rate. So this information, the same information is repeated 3 times. It is redundant information. So PCM signals contains redundant information, right? And this is a big problem because it is going to increase the bandwidth required for the transmission of this signal, right? You can also see here these 3 signals, again they are same, right? So these signals, when they are same, then what is the need of taking samples, same sample again and again, right? What is the way of sending 1 to 3, 1 to 3, 9 bits, right? Instead we can send us 3 bits only, right? That will do the purpose, that will serve the purpose. Here's the same thing. So this is the problem, this is major problem with the PCM, right? Redundant information, and the another problem that I discussed, that was the noise, distortion, right? So all these things lead to the requirement of high bandwidth, high bit rate. Because of these drawbacks, this PCM, pulse code modulation, is rarely used, but we have a new type of pulse code modulation, that is called differential pulse code modulation. That is going to remove the difficulties arising with this one, right? So in the coming lecture, we will discuss the differential pulse code modulation. So this is all about the pulse code modulation, right? So thank you very much.